During the first lesson, we have described the main concepts of electrochemistry, or better, well, just the difference between a galvanic cell and an electrolytic cell. But actually, what is the difference? We already know that, but what is a cell? So, a cell in electrochemistry is that instrument made of different parts and components useful in order to, in the case of a galvanic cell, transform chemical energy in electricity, or the opposite in the case of electrolytic cell. So, what is a cell? And which are the components of a cell? So a cell is composed of electrodes that are basically the place where actually the reaction occurs, the electrolyte necessary in order to close the circuit due to a movement of charge, and then an external circuit. Actually, the external circuit is not exactly a component of a cell, but is necessary in order to close the circuit, because when we want to obtain useful work, we will see this concept better speaking about thermodynamics of electrochemistry in next lessons. But when we want to obtain useful work, we need an external circuit, because we need a resistance. We need to discharge electricity on a resistance in order to obtain useful work that we can exploit for different action and derive all the function of our device. So we have a cell that is composed of, so we have a cell described as place, instrument, in order to promote an electrochemical process, and is made of two, better, not exactly, because we have even a reference electrode, but we will see this later, but we have in general electrode, electrolyte, and external circuit, if we want to derive electrons closing the circuit and take advantage of this chemical energy. So, at the very beginning, it's important to clarify what is an electrode, and in particular, what is the difference between, even if this it will be more clear speaking about reference electrode, thermodynamics of electrochemistry, Pourbet diagram. I want to treat all these topics in the next lessons, but now I need to ask for an imagination's effort in order to understand what is the difference between the electrode potential and the total potentials of the cell, because the potentials of one electrode is not at all the d.d.p of the cell. That is just the difference between the potentials of one electrode and the potentials of the second electrode, because we need to have at least always a working electrode and a counter electrode. So in a cell, let's imagine for a while, to avoid the presence of resonance electrode, we will see what is the reasons for which it's important to have a reference electrode, especially in the electrolytic cell, when we want to apply a certain potential difference. What we need to say is that we have a working electrode, so a first electrode, and a counter electrode, another one, are connected with the external circuit. Obviously, we need to have a resistance. Why? Because if a resistance miss here, we have just a pathway of electrons without any types of obstacles. And so we are in a short circuit condition, because we have a pathways of a movement of electrons so strong that without resistance that can maybe cause some damage, for instance melt the wire, or in any case we are not able to take advantage of any types of energy without a resistance, because the resistance is the place where actually we are taking advantage of a current and we use this current for something. For instance, the movement of electrons through the resistance is able to heat the resistance, and this heat can be used in order to, or converted, or maybe it could be even able to create radiant energy. So the resistance is the bridge that allows us to use electricity in order to create an actions, a mechanical actions, or light, for instance. If the cell is the bridge between the chemical reaction and the electricity, the resistance is the bridge between the electricity and something more that is useful for us. This is the reason for which we are always able to observe at least or a voltmeter or a resistance in the different scheme representing a cell. Then we have the electrode and the electrolyte. So electrolyte, this one, so electrolyte is something that is a medium. It could be a liquid, it could be an aqueous solutions, or an aprotic solution, for instance in lithium-ion battery, in which the presence of water is a really important hazard. Or it could be even a solid, for instance in fuel cell, speaking about proton exchange membrane. What is important in this case is consider that electrolyte is a medium that, regardless the physical state, is able to drive the movement of ions, not electrons, because electrons follow always a pathway that is through the external circuit, always, but never inside the electrolyte. So electrolyte, from a theoretical point of view, is something that closes the circuit, but it closes the circuit only because it's able to veiculate the movement of ions and never electrons. This is obviously quite simple. Just imagine about the Faraday's cage, in which we are protected just because the electrons prefer to follow the cage, since the resistivity is smaller. Well, the same concept is present here. Electrons follow this pathway because electrolyte cannot allow the passage of electrons. And so we will see in a moment with the descriptions of electric as a double layer actually what does it mean that an electrolyte is able to close the circuit due to a movement of ions. We will see this later with a graphical picture, a representation. So together with the electrolyte, the external circuit, we have the two electrode, the place where actually the reactions occur. And in particular, in galvanic cell, for instance, now we are speaking about a galvanic cell, we have always, but this is also true in an electrolytic cell. So in general, we have always an anode and a cathode. So we have a place where the reduction reactions is occurring, and we have a place when an oxidation is occurring. So in the cathode, we have that electrons are collected from the external circuit in order to promote the reaction of one species. And so, for instance, we have something like this that is going in this direction. Whereas in the anode, we have the opposite. We have that one species is oxidized in order to release electrons. For instance, it could be a metal, and this it could be oxygen. This is the principle of metal-air battery. Basically, we have a species. It could be, I don't know, for instance, zinc or copper. Let's make, for instance, about copper. Or zinc. And we have the release of electrons due to the oxidation. So we have, for instance, zinc 0 and zinc 2 plus, and the release of 2 electrons. Whereas here we can have another species. We can have, for instance, a reduction reaction, maybe oxygen. And in this way, what is actually occurring, that we have the release of an oxidized species here, the generations of electrons. These electrons are collected in order to transform molecules, for instance, in this state here, in a reduced one. This is how actually a cell works. It's a redox reaction, but it's not a redox reaction in which the reagents are close one to each other, but is something similar. So here the final result is the same, but the reagents are not close, are one present on one electrode, the working electrode maybe, and the other one is present on another side. So one reagent is here and one reagent is here, and the electrons need to follow this pathway in order to ensure the creations of the reaction. But it's nothing different, it's a redox reaction. But the way in which we are allowing the possibility to promote these reactions due to an external circuit allow us to take advantage of these redox reactions, because the electrons are following a pathway on which we can place a resistance that can be used in order to make work. So, but now it's important to understand what is the difference between an electrode potential and the total potential of the battery. And in particular, this is important because know what is the meaning of electrode potential allow us to understand why we have the oxidation of this species and the reductions of this one, and not maybe the opposite. So it's just a matter of thermodynamics. Some species are more able to be oxidized and other ones are more able to be reduced in specific conditions. And the tendency of this type of species in a or couples, in general we are speaking about when we're speaking about potential, a reduction potential, we are referring to one species and the corresponding reduced one. But this is not important now, I don't want to make confusion, this concept will be more clear later. But in general, the potential, the electrode potential, not the total potentials of the cell, but the electrode potential is a measure that allows us to understand how much a species prefer to be oxidized with respect to reduce. And so since we are dealing with electrons, when, as a convention, when we have an electrode that is based on a reaction having a higher, a more positive potential of electrode, and we have here, for instance, another electrode having another reaction, but here the potential is smaller, well, electrons, since we are dealing with negative charge, prefer always to following this direction. So we have that the electrons pass from a smaller potential to a positive one. So we have an electrode and we have a specific semi-reaction associated with this electrode. And these semi-reactions is connected with a certain specific reductions potential. And the same for the other one. But the value of these potentials allow us to understand what it will be the spontaneous flowing of the electrons. If this potential is higher than this one, we have this pathway. If the opposite, we have the opposite pathway.